To learn more about earning college credits with study hall courses, visit gostudyhall.com or click on the link in the description. Analogies are really helpful tools for trying to relate these super specific quirks of programming to the real world, and I've got another one for you. A program is like a finely tuned professional kitchen. Well, at least part of it is. After you order your lasagna or tea, the order gets passed between the front of house staff to the kitchen full of people who all have their own list of smaller tasks to complete. Eventually, a delicious meal arrives right in front of you. And efficient restaurants have systems, or dare I say, methods, that simplify tasks, minimize repetition and overlap, and make it all possible. The same is true for methods in programming. Methods pack a lot of punch in a simple structure. They're a block of code that we can call back to throughout a program when we need to do the same thing again and again. But there are a lot of points where things could go wrong. So just like it's important for a restaurant owner to know what everyone on their staff does, from ordering groceries to plating, it's important for us programmers to build a deep understanding of how methods work. This way, we'll be ready to debug all kinds of problems that will inevitably appear in our code. I'm just being realistic here. Nobody's perfect, and mistakes, they happen. Hi, I'm Sabrina Cruz, and this is Study Hall, Code and Programming for Beginners. It's brunch time at the Raton Cafe, which is run like a well-oiled computer program. There's a whole person taking orders from the waitstaff, calling out those orders to chefs in the kitchen, and sending out completed dishes to the dining room. At Raton, that's Colette. When Colette calls out an order, she's basically addressing another specific chef who manages a smaller subset of tasks. For example, she might call out a house salad with chicken. Then it's the salad chef's responsibility to prep and return the completed salad to the window where it's ready to be delivered. Basically, the restaurant is the computer, and Colette and all of the other chefs are all methods in our program. Here's what the salad ordering and making process might look like if we translated it into Java methods. Well, kinda. Before you come at me with, Sabrina, what the heck is this word salad? This is pseudocode, which programmers use to plan out the logic of a program before diving into the real code or a program that would actually run. We're exercising our creative license here, and we know that salad obviously isn't a data type. Yet? First, we write out everything that the salad chef does in the make salad method, which has all of the specific instructions that they follow to produce a finished plate. And just like Colette calls out orders in the kitchen, next we have the main method that represents Colette. It calls and runs other methods. Now, methods are great for tasks that have to be repeated, but each time we can personalize it a little. So inside of the main method, when the make salad method is called, we can add chicken as the parameter topping. That's like Colette telling the salad chef to add chicken when the order is called. In general, Java's compiler processes each method call according to the rules of the programming language and a specific method signature. A method signature is a description of the method, including the method name and any parameters we can customize. So in this case, the method signature for the make salad method would include the name, which is make salad, and the input, which is the string argument chicken. And there would be an entirely different signature that the Java compiler would process for a method named make tea. Whenever any method is called, Java's compiler matches it to the method signature created when the method was first declared, just like how Colette matches an order to a particular chef. That's how Java knows which set of instructions to follow, and how a computer would avoid mixing instructions and delivering a cup of hot Earl Grey tea with a chicken nugget on the side. Nobody would want this! Thank you. In addition to storing method signatures for every method in a program, the computer does a lot more heavy lifting every time we call a method. Going back to the Raton Cafe and a restaurant as program metaphor, one of Colette's other responsibilities is to take inventory before brunch service even starts. Today, she needed to decide which mushrooms to use in quiches, either shiitake or portobello mushrooms. Colette chose the mushrooms that she had the most of in storage. Using that scenario as guidance, here's how Colette's decision-making would translate to a Java program. A real one, by the way, not pseudocode, because it turns out comparing numbers is easier than making a chicken salad with code. The inputs are pounds of shiitake and portobello mushrooms in the fridge. In our code, we'll store them as doubles in case we need to account for decimals. Then we can call the math.max method to return whichever number is bigger and print it out. By the way, adding units to your print statements is always a good practice. Otherwise, how will you remember what you're measuring? Pounds? Kilometers? Tea bags? It could be anything. So that's what we see when a Java program runs, but there is so much more happening under the hood. Here's how it works from the computer's perspective. When we call the math.max method, we supply shiitake pounds and portobello pounds as arguments. So first the computer retrieves the values of those variables from memory. Next, the computer sets up a method context, which is a controlled environment that helps each method execute independently. Think of a method context like having separate stations at the Raton Cafe. Just like we want the salad and drink stations to be separate to avoid mishaps like an Earl Grey chicken latte, we also want methods in the computer to operate without interfering with each other. In programmer jargon, we say that the scope of method variables is confined within each method context. In other words, each method context uses a different section of the computer's memory to store the arguments that are supplied to each method call, so that those variables can't be accessed from other parts of the program. That way, we can avoid any pesky interferences or mixed messages. You can check out our first episode on methods for a refresher on all of those terms, like method arguments and scope. But back to our mushroom program. In this example, setting up the method context means the computer basically creates placeholder 1 and placeholder 2 as variables in a specific section of the computer memory. After that, the computer can supply those retrieved argument values of shiitake pounds and portobello pounds, 12 and 15 respectively, to those placeholders. This process is called passing an argument by value, because that's exactly what we're doing, replacing the placeholder variables with the argument values that represent our mushroom amounts. Once the method context is finally set up, the computer can execute all the instructions inside of the method until it reaches the return statement. Just like a dish needs to be plated before being served, a return value needs to be placed in a register to capture and store it before it's returned. At the end of the mushroom example, we store the return value of the math.max method to a double variable called chosen mushroom amount, and the method returns the maximum mushroom amount of 15 pounds, which will be used to make some delicious portobello quiche. So far, we've been talking about method calls that handle one main process, but when a process gets really complicated, we can break it down into simpler sub-processes, and that's where multiple method calls come in. This is sort of like combo orders at the Raton Cafe. When Colette calls out one order for a caprese sandwich and a side house salad with added chicken, she'll need two chefs to make that happen, the sandwich chef and the salad chef. Here's how we might translate that to Java, if we stretch our imagination a bit and use some pseudocode. Remember that each chef is represented by their own method, so we have make sandwich and make salad, which are reusable for any sandwich or salad type. Next, we have a make order method, which calls both the make sandwich and make salad methods, with specific arguments for caprese and chicken respectively. Finally, we reach the main method, and all we have to do is call make order once, which calls make sandwich and make salad so that both components of that order get done. It can be a little tricky to get used to this logic, but we format the code this way because we don't want one method performing a lot of different tasks, the same way you don't want one chef cooking everything in the kitchen. That's a recipe for disaster. Multiple method calls get a little more complicated from our perspective, and there's even more going on under the hood too. Specifically, the computer uses a call stack to keep track of all of the method calls in a program. A call stack is a pile of subtasks that the computer will need to work through in order from top to bottom. This structure is similar to the stack trace we talked about in our episode on debugging code. Anytime you hear the word stack in programming, think of a stack of cards that you draw from the top, one at a time. Java's call stack is a pile of method context. The first method we call is the first card we add to the stack, and each method we call after that gets added on top. So the topmost method on our call stack is always the one that is currently running, and once that method finishes, the computer removes it from the call stack and begins working on the next one. And this is important when we're creating and organizing our code. We want it to run how we expect. Here's how the call stack works for our caprese sandwich program. Java code always starts with the main method, so that one is the foundation of our stack. Inside of main, we call make order, so that method context gets stacked on top. And then inside of that method, we call make sandwich and make salad, so they get put on top in that order. Technically, the make sandwich method will finish and then the make salad method will get called, but you get the idea. The main thing to remember is that the last method we call is the first method that gets run by the computer. In other words, we need to make the sandwich and the salad to make the order, which is what the main method, aka Colette, asked for. Call stacks work the same way for methods that call other methods, like this example, and for methods that call themselves, which we learned about in our episode on recursion. A deeper understanding of how those method calls work and how they work together will help us catch all kinds of errors in our code. Like maybe we forgot to input an argument value, so the computer had nothing to store or retrieve from memory when it set up a method context. Or we forgot to call a method inside main, so the call stack never piled up, and the computer doesn't have any instructions to follow. With a little practice, we can predict how a computer will behave in almost any situation involving a Java program, and become better problem solvers who fix bugs before they even happen. Instead of blindly copy-pasting code that might work, we want to be the kinds of programmers who understand what we're doing every step of the way. You almost got me! If you're enjoying Study Hall Code and Programming for Beginners and are interested in taking an online course and earning college credit, check out gostudyhall.com or click on the button to learn more. Thanks for watching, and see you next time.